Warning: hydrochloric acid and oxalic acid are corrosive. Hydrochloric acid vapors are irritating. Wear gloves when handling them. Hi, here is MIH. In the first experimental video in this channel, I made hydrochloric acid using sodium chloride and sodium bisulfate. However, hydrochloric acid is a very useful chemical, and I need it in relatively large quantities. And this is why I devised a more convenient method in this video. We are going to need oxalic acid and calcium chloride today. Oxalic acid and sodium chloride also work, but the reaction cannot be done in aqueous conditions and instead must be heated dry. The produced hydrogen chloride gas is then dissolved in water to make hydrochloric acid. Because the method involves gas absorption, the yield is also considerably lower than the method we will be using. However, the method is still doable if sodium chloride is all you got. Anyways, for our method, measure out 63 grams of oxalic acid dihydrate in an 150 milliliter conical flask. Place the flask on a hot plate stirrer and add about 80 milliliters of boiling water to dissolve it. Make sure that the water is boiling since oxalic acid is not very soluble in room temperature water. I originally planned to use 60 milliliters, but the acid did not completely dissolve, so I added 20 milliliters more. Try to use a minimal amount of water here. While the oxalic acid is dissolving, measure out 55.5 grams of anhydrous calcium chloride. You can also use hydrated calcium chloride, just adjust the stoichiometry a little. Then add 80 milliliters of boiling water to it. This must be done in small portions because anhydrous calcium chloride releases a lot of heat when it dissolves and will boil the water. You can see that the first bits of water were completely boiled away. When all the water is added in, the calcium chloride should dissolve quite easily. I stirred it around a little until it all dissolved. The concentrated solution appears slightly viscous when stirred. There are some brown impurities in the solution, but that is fine and would not impact the reaction. I waited for the last bit of oxalic acid to dissolve. When it completely did, and the solution was crystal clear, I prepared a silicone stopper fitted with a tube and a glass rod. This is just to keep the stopper airtight. The silicone stopper must seal the conical flask perfectly. Then I poured the calcium chloride solution slowly into the oxalic acid solution. A milky white precipitate of calcium oxalate immediately formed. Here, the calcium chloride is reacting with the oxalic acid to produce calcium oxalate and hydrochloric acid. I did not pour all the calcium chloride in since I found that my flask wasn't big enough to hold all of it. Instead, I simply stoppered the flask with the silicone stopper. Notice that this reaction is reversible, meaning that the calcium oxalate can also dissolve in the hydrochloric acid. Here we are taking advantage of the extremely low solubility of calcium oxalate in water to drive the reaction forward. When the stopper is taken off, you can clearly see the hydrochloric acid vapors released from the hot solution. For this reason, work in a well-ventilated area and avoid inhaling the vapors. I added some more calcium chloride and took the flask off the hot plate to cool. This is a time lapse of the cooling of the flask. Notice the textures on the side of the flask and the slowly decreasing volume. Here is the flask after 30 minutes. Most of the calcium oxalate had settled to the bottom, and the solution was only slightly warm to the touch. I transferred the flask to an ice bath. After a few minutes, I took the flask out and proceeded to a vacuum filtration. I took the stopper off and transferred the upper water layer to the funnel. The vacuum pump is turned on, but the filtration still proceeds terribly slowly. Additionally, the filtrate wasn't perfectly clear and likely still contains some residual calcium oxalate. In hindsight, I should have directly poured out the water layer and filtered the leftover residue. Then I can get some pure concentrated acid and wash the residue with more water to obtain some dilute acid. Anyways, a useful tip is never filtering calcium precipitates, especially the sulfate and the oxalate, because they can easily clog the filter and make the filtration proceed very, very slowly. Instead, simply let the mixture settle and decant off the upper water layer. I washed the flask with some water to take up the remaining acid as well as calcium oxalate. I shook the flask strongly and transferred its contents to the filter as well. Afterwards, after trying to improve the filtration rate and failing miserably, I decided to transfer the contents inside the funnel back in the conical flask. This resulted in a bunch of spilling and a mess that I must clean afterwards. You can see that there is a huge lump of white material sitting in the filter. I originally thought that I removed the filter paper along with the calcium oxalate, but on further inspections I realized that the chunks are pure calcium oxalate. No doubt that the filtering took a tremendously long time. In the end, I was able to obtain some crude, murky acid and a bunch of white calcium oxalate. I then attempted to distill my acid to purify it. Here is my glass distillation apparatus, which took quite some time to arrange because it was tremendously large. I attached a thermometer in place of the glass stopper and ran some cooling water into the condenser. I then poured in all my acid and started the heating. Unfortunately, my hot plate wasn't very powerful, and the acid heated at a ridiculously slow pace. You can also see that the acid is visibly yellow, which is very weird because it wasn't that yellow in the preceding steps. I'm now pretty sure that it was the silicone stoppers that contaminated it. After waiting for about 30 minutes, the acid barely boiled. I decided to stop the distillation and transferred my acid directly into the storage bottle. I let the storage bottle cool to room temperature. As for the leftover calcium oxalate precipitate, I transferred it to a large beaker and shook it around with some extra water. I then covered it with a plastic dish and let it settle. After it settled, I pour out the water layer into a storage bottle. This extra water washes out some of the remaining hydrochloric acid, so now I can get some dilute hydrochloric acid for use as well. Anyways, we can now measure our yield. I poured 50 milliliters of our concentrated acid in a graduated cylinder. Its mass happens to be 54.32 grams, which corresponds to a density of 1.0864 and represents a concentration of about 17%. I made a total of 74.14 grams of acid in the reaction, so our total yield is then about 38.6%. Well, honestly, I probably can get it higher by a lot. This yield only corresponds to the concentrated acid we got first time, and there are certainly a lot of acid still in the water washing we did later. I also lost a lot of hydrogen chloride in the distillation step. In conclusion, the great advantage of this method is that it is extremely cheap and can be easily replicated. I can accept a slight lower yield in exchange for that. Additionally, the yield can be improved very easily by increasing the concentration of the reactions and minimizing the amount of water used. Anyways, this method will be the main way I get my hydrochloric acid in the future. Thanks for watching.